Hello students, welcome to the lecture 12 of STA201 Elements of Statistics and Probability. This is Mirza Tanjim Shorif Mugdho, and today we'll study application of combinatorics in solving conditional probability problems. So we'll start with the statement of a problem. Let's see the statement. So this is the question. The question says that suppose you have 5 fair coins and 10 unfair coins in a bag. Each of the unfair coins has the probability to show a head equals to 0.8. Okay, and 0.2 is the probability for an unfair coin to show a tail. Now suppose you randomly picked a coin from the bag, so you don't know whether it's fair or unfair, and then you flip it for 6 times. Let's say you got 4 heads out of your 6 flips. So you have to determine the probability that you flipped a fair coin given that you got 4 out of 6 heads. I'm repeating again, you have to find the probability that you flipped a fair coin given that you got 4 out of 6 heads. To solve this problem, we need to remember a few data from this question. So there are 15 coins in total, 5 fair coins. 5 fair coins means each of the fair coins have the probability to show a head equals half, and for tail it will also be half. And then for the unfair coins, the probability to show a head is 0.8 and it's 0.2 for tail. Now you picked a coin randomly, you flipped it for 6 times, you got 4 heads out of 6 flips. So you have to determine the probability that you flipped a fair coin given that you got 4 out of 6 heads. Now for the solution, the first thing we have to do is to name the events properly. Okay, so let's say A equals the event of picking a fair coin. Okay, so this is A, and B equals flipping 4 heads out of 6. So to simplify it, we'll write it like 4 out of 6 heads. Okay, all right, now we have to determine P of A given B. Now this is a conditional probability and we are going to use Bayes' theorem to solve it. We know that P of A given B equals P of A intersection B divided by P of B. So to determine this probability, we have to find P of A intersection B and P of B. So let's start with P of B. So P of B is the probability of getting 4 heads out of 6 flips. To determine the probability of getting 4 heads out of 6 flips, we have to know the type of coin that was flipped in the first place. So we need to know the type of coin, whether it was fair or unfair. Therefore, we can write that probability of B equals to probability of picking a fair coin from the bag randomly and then flipping 4 heads out of 6 plus probability of picking an unfair coin from the bag and then flipping 4 heads out of 6. So this is the total probability theorem from your conditional probability lecture. I hope you remember it. So to determine P of B, we have to determine P of A intersection B and P of AC intersection B. From tree diagram, we can say that the probability of picking a fair coin from the bag is 5 by 15 because there are 5 fair coins and total number of coins in the bag is 15, and for unfair coin the probability will be 10 by 15. Okay, because there are 10 unfair coins, so it's 1/3 and it's 2/3. Now for fair coin we'll have a probability, and for unfair coin we'll have a probability of flipping 4 heads out of 6 flips. Okay, so here will be another probability, and then finally to determine P of A intersection B we have to multiply this probability and the probability here. So let's start with fair coin. Okay, so what would be the probability of flipping 4 heads out of 6 flips with a fair coin? So now we know that flipping a head has a probability half for a fair coin, so it's P of H, and P of T equals to also half for fair coins. Now we are going to determine the probability of flipping 4 heads out of 6 flips. Okay, so let's start with 6 free boxes where there will be 4H and 2T in these boxes. Okay, so if I put H in the first 4 boxes and 2T in the last 2, then it means that the first 4 consecutive flips showed H and the last 2 showed T. This configuration actually satisfies my condition because there are 4H and 2T here, and there are some more configurations like TH, H, T, H, H. Okay, so it also has 4H and 2T here, and there are many configurations. Okay, so now we are going to determine the probability for each of these cases or configurations, and finally add all of these probabilities to determine our result. So for the first case, we have the first, second, third, and fourth showing head. So the probability for the first flip to show head is half. For the second, it's also half, third half, fourth half, and for the fifth flip, it will be 1 minus half, right? Because it showed tail here. And for the sixth, it's also 1 minus half. So finally, it's half to the power 6, okay? Interestingly, the second case will also give us a probability of half to the power 6. How? Let's start. If we say that the probability of the first flip to show a tail is half, then second is half, third half, fourth half, right? The first and the fourth for tail, and the remaining are for heads. So it's also half to the power 6. So we will get half to the power 6 for all such possible configurations. Now, if we add all of these probabilities, we will get our final result. So how many configurations are there where there are 4H and 2T? In other words, we can say that in how many ways can we fill up these 6 boxes where there will be 4H and 2T? Or we can state this problem like this, that how many 6-letter words are there where there are 4H and 2T? So it's very simple because we've already studied it in our combinatorics lecture. So we can take help from the theory of permutation of repetitive elements. So if all of these letters were different, the 6 letters were different, then the answer would be 6 factorial. But there are 4 repeating elements, 4 repeating H, therefore it's 4 factorial and 2 factorial, okay, for 2T. Now this is equivalent to 6C4, right? So there are 6C4, which means 15 cases. If you calculate 64, it will get 15. So there are 15 cases where the probabilities of each case is half to the power 6. Okay, so we are going to add 15 number of half to the power 6s to get our final probability. That means 64 times half to the power 6 is the probability. This is the probability of flipping 4 out of 6 heads with a fair coin. So we are going to put this probability in the tree here. Okay, so this is 6C4 times half to the power 6 here. Now for the unfair coin, we can do the same. All right, so for an unfair coin, we will have 6 boxes where 4 of them will be filled up by H, 2 of them by T. So say H, H, T, T, H, H is a configuration, and for an unfair coin, we know that P of H equals to 0.8 and P of T equals to 0.2. Now this probability is 0.8 times 0.8, 0.2, 0.2, 0.8, and 0.8. So this is the probability of this case to happen in case of an unfair coin. So it's 0.8 to the power 4 times 0.2 square. Many cases like this where there will be 4H and 2T. So we've already calculated in our previous part. So it's 64 because there are 64 number of ways to fill up 6 boxes with 4H and 2T. So all of these probabilities will be same, just like the last one. So 64 times 0.8 to the power 4 times 0.2 square. So this is the probability of flipping 4 out of 6 heads with an unfair coin. Okay, so let's put this probability in the tree again. Here's the tree. So it's 64 times 0.8 to the power 4 times zero point 0.2 square. I hope I didn't make any mistake here. Yeah, so 0.2 square. So to get P of A intersection B, we have to multiply these two probabilities. That means 1/3 times 64 times half to the power 6. Similarly, for P of AC intersection B, we have to multiply these two probabilities. Okay, so it's 2/3 times 64 times 0.8 to the power 4 coming from 4 heads from an unfair coin, and it's 0.2 to the power 2. It's very simple. So now for P of B, we have to add these two probabilities. All right, so finally we'll have P of B equals to 1/3 64 half to the power 6 plus 2/3 times 64 8 to the 4 and zero point 0.2 to the 2. So this is the probability of B. Now for P of A given B, we need P of A intersection B as well. We've already determined the denominator. Interestingly, we've already determined P of A intersection B because this is the numerator of the fraction we were interested in. So P of A intersection B is already determined. Therefore, the final probability is like 1/3 64 times half to the power 6 divided by 1/3 times 64 times half to the 6 plus 2/3 64 0.8 to the power 4 times 0.2 square. So if you calculate this fraction, you will have a probability. Sorry, it's a little clumsy. So 0.3227 8. Okay, so this will be the probability.